Okay, on to dipole moments. Dipole moments. Property of a molecule whose charge distribution can be represented by a center of a positive charge and a center of a negative charge. So you have two charges on different sides, hence creates a dipole. Di meaning two, pole meaning poles, ends of the molecule. We use an arrow to represent the dipole moment. You've seen it previously. It's the arrow and then it has like the little cross at the end like so. You point the arrows towards the more electronegative area where the electron density is going to be greater. Okay, the tail of the arrow is going to be at the positive center where the electron density is less. All right. So, for example, for water here. Hopefully you remember that water is a nice vent-shaped molecule here. Okay. And electron density, these graphs here are the nice, like the blue is the side that is the partial positive side, and the red over here is the partial negative side. More dense electron around that particular side. Now, due to the fact that water, of course, is a polar molecule, it has a huge electronegativity difference between oxygen and hydrogen. It's like 1.4 or something. You don't have to calculate that. I just know that one off the top of my head. So it is fairly on the higher end of the polar side of the spectrum. Now, this middle diagram represents the dipole 2, showing that this is the negative side, this is the positive side of the molecule. That's one way to do it. You can draw the dipole just that one direction, like so. But usually, when we have a bent-shaped molecule like this, we draw the dipoles towards the more electronegative element. So like here, I would draw it this way, towards the oxygen, this way, towards the oxygen. This therefore indicating the partial negative side is right at the oxygen, and then the partial positive side would be over here somewhere. Now, of course, the way they label it is based off of the atoms here in this particular ball and stick model. Okay, but yes, if we were lining them up in the electric field, the hydrogens would face towards the negative plate, as you see here, and the oxygen would face towards the positive plate, because that's where the partial charge alignment would put the attractive forces. Because the negative side would attract the positive plate, the positive side would attract the negative plate. So you could draw it either way, the directional, like right towards the oxygen, or you can draw them up from the hydrogens into the oxygen. There's a couple different ways to represent the dipole moments. Now, we know water is a polar molecule. We do know that it has a dipole moment that goes one direction, and that it definitely creates distribution of charge, higher density of electrons around the oxygen than around the two hydrogens. Let's look at an example where this doesn't occur. There is no dipole moment. Does everybody remember carbon dioxide? Carbon dioxide, we draw the Lewis dot structure as a nice linear molecule. It has the double bonds, right? The two dots. Okay, don't worry. And my lines, of course, got a little skewed there, so I think it's the way the smart bar is going. Let's draw that again. There we go. Okay, so nice linear molecule, 180 degrees around the central atom. Don't forget, too, like the way that they create their shapes is based off of the VSEPR theory, where they space themselves out to be as far apart from each other as possible because electrons repel each other. So that's why we get these basic shapes. The bent-shaped molecule of the water is because it has the two lone pairs, the two bonded pairs. Here, this one just has the two bonded pairs. It's a linear molecule. Like I said, we'll get back into shapes and drawing a little bit later, but for our purposes, what you should see here, even though we know, if you look at our periodic table, that there's a difference between carbon and oxygen, so that it is a polar bond. I mean, you could calculate it with the electronegativities. I believe the electronegativity difference between carbon and oxygen, if you did calculate it, would be 1, so it would be smack dab in the middle, polar. But if you just look at your periodic table, you know that it is a polar bond. C to O is a polar bond. However, based off of the way that the shape of this molecule is, this one happens to be a non-polar molecule. Now, non-polar molecule with polar bonds. nonpolar molecule with polar bonds. If you draw the dipole moment in, dipole moments go towards the oxygens, like so. So basically what happens is the electron densities, the oxygens are pulling equally hard on those electrons, so the electron densities are the same at both ends. So therefore you do not get a dipole. You don't have an unequal distribution of charge. You don't have one end that's partially positive and one end that's partially negative. So this is what we say, the dipoles are canceling out. The dipole moments are canceling out, so there's no net dipole. You don't have one direction where the electrons are spending more time, or there's more of a density. Okay, so carbon dioxide is nonpolar, basically because of the way it's shaped, because that makes the dipole moments cancel out. Now I know in Chem 1, we always talk about it in terms of symmetry. How is it shaped? If it's symmetrical, then it's going to be nonpolar. Well, the reason why we can say that when it's symmetrical like that, it's really because the dipole moments cancel out, and it renders the entire molecule nonpolar. So when you have no net dipole moment, dipoles cancel, it's going to be nonpolar. That doesn't mean it doesn't have polar bonds in there. Carbon dioxide has polar bonds, but the entire molecule itself is nonpolar. Let's look at a few more examples. I like this comparison too. Okay, so this is chloromethane, and that's tetrachloromethane. Don't get that name confused. That's just the organic name for it. Technically, you could call this one over here on the right carbon tetrachloride using the regular IUPAC naming system. But here, one carbon organic molecules, they have meth prefixes, so these are both named through the organic naming system. Now there is a difference between them, as you can see. We have one over here. This is like CH3Cl, that's the formula. And you see that obviously chlorine is going to be more electronegative, and you have a dipole moment that goes towards the chlorine. They show that in here with the electron density and the big red up there. So electron density is higher around the chlorine. That means it has a dipole moment. And here you can numerically calculate dipole moments, although for AP they don't have us do this. Sometimes they put the dipole moment data in tables for you to read. So if you see a little mu here for chemistry, mu means a lot of things. It means micro in biology, it means friction in physics, but here it means dipole moment. And here 1.87 dipole moment, this is a polar molecule. In comparison to our carbon tetrachloride or tetrachloromethane, whichever way you want to call it, as you can see, the dipole moments, you would have dipole moments between all of the carbons or the carbon and all of the chlorines. Each bond would be polar here, but because it is tetrahedral shaped and it's symmetrical, the way it spaces out around the central atom, those dipole moments are going to cancel, and this is going to have no net dipole moment. And as you can see, the measurable here, it's 0. So this is a nonpolar molecule. All the ligands are the same. Remember, the ligands are the outside atoms. If all of them are the same and there's no lone pairs on the central atom, all the dipole moments will cancel, and you have a nonpolar molecule. If you have a dipole going one direction and it doesn't cancel, you're going to have a polar molecule. And as you can see, like they put all the red around the edges because those chlorines are all equally trying to attract the electrons towards them. So the electron density really around all of the chlorines is pretty much the same. Okay? Now here is another depiction of dipole moments. I didn't put this in your notes, but I just wanted to show you a few more examples and other various shaped molecules. Obviously, hydrogen chloride, it only has 2 atoms in it. It's going to be linear shaped, and the dipole moment is going to go towards the chlorine because it's more electronegative, and definitely that one is this one's going to be polar right here. Okay, that's a linear molecule because it only has 2 atoms. Now the boron one is kind of interesting. Remember, boron doesn't always follow the rules. Like I said before, boron is stable with 6 valence electrons. So it forms this like trigonal planar shape. Trigonal planar shape, the dipole moments cancel. We end up with a nonpolar molecule there. This one is formaldehyde. Okay, So it's CH2O. As you can see, the dipole moment points towards the oxygen, the more electronegative element. So this side of the molecule is going to be partially negative, this side of the molecule is partially positive, and we definitely have a polar molecule and a net dipole. Ammonia is also a classic one here, NH3. All the dipole moments point towards the nitrogen, and we definitely have a partial negative up here and a partial positive down below where the hydrogens are. They're the mini part of the pyramid. The shape of this one is T pyramidal. I don't know if you remember that. It forms kind of a mini pyramid because there's a lone pair that sits on top of the nitrogen. Don't worry if you're not remembering the shapes. I'm going to go and do the shapes in detail later on. Here is another one of the tetrahedral carbon tetrachlorides. This is a tetrahedral shape. They cancel out. Okay. Whereas this one, similar to the one on the previous page, except for it had 3 H's and only 1 chlorine. But as you can see, this part would be partially negative. Up here would be partially positive. Also tetrahedral shape, but the ligands are not the same, so you do have net dipole that goes in one direction. And this one, this is phosphorus pentafluoride. This is a bipyramidal shape. I'm going to write that wrong. Hold on. Bipyramidal. This is one of those expanded octet ones, okay? And there aren't any lone pairs on the phosphorus, so really basically all the dipole moments point towards the fluorines and they cancel out. Last but not least, sulfur hexafluoride is the octahedral one, also an expanded octet here, and they all point towards the fluorine. There is no lone pairs, so this one ends up also being nonpolar, no net dipole. All right, so let's talk about some of the gray areas here, okay? And we know like H to F, H to O, and H to N creates very large electronegativity difference because those are the 3 that are able to do hydrogen bonding in their IMFs, and that's created because they have huge electronegativity differences. So if you look here, you see HF. It's kind of out of place. This graph tells you electronegativity difference across the X, and it's also looking at the percent ionic character. So HF seems to have quite, shifted over the electronegativity difference, not as high in the ionic character, but it does seem like it belongs in the other group. So why do we not put HF in the other group? This is why. Even though the electronegativity difference seems like it should be placed there, it really doesn't have any of the other properties that ionic compounds do. So ionic compounds, they can conduct if they are melted. They can conduct in water. They are brittle as solids and things like that. And they have really, really high melting and boiling points. All of these physical properties of ionic compounds, HF does not fit that operational definition. It does not work with it. So in order to really put it in its correct group, we also must take a look at the physical properties. Okay, so why isn't it classified as ionic? A compound that conducts an electric current when melted is classified as ionic. That is one of the main distinguishing properties of an ionic compound. So since it doesn't fit that definition, we still put it in the covalent category. And the best way to classify bonds, like the electronegativity piece is just one piece of information. And yes, it gives you a general idea of things. It's a good one to use, but we really also should know a lot about the properties of what we're talking about here. Okay? So the best way to classify the bonds is based on the examination of the properties. HF is one of those in-betweeners, and there's a few that are in-betweeners, and like I'm sure you've already figured out that in AP Chemistry, you get these general rules, but there's always a few little ones that are in the gray area that don't necessarily fit in any particular spot. Okay? All right, so let's talk about metallic bonding, and we'll talk more in detail about metals later when we get to the solids category. But what is metallic bonding? It is described as a group of cations suspended in a sea of delocalized electrons. This model explains metal properties, okay? The electrical and thermal conductivity, ductility, and malleability of metals. So, basically what you see here is what you need to identify as the metallic bonding diagram. What you're going to see in a metallic bonding diagram is a bunch of positives all in orderly fashion. Nice, orderly fashion. What you'll see here is a bunch of dots that look like they're randomly scattered around them. The randomly scattered around dots are the delocalized C of the valence electrons. So, the electrons being delocalized, they can attract and be moved and have free flow. That's what's giving them those extra metal properties, the conducting electricity and heat. The malleability, you can pound it, you can form it into wires, that's ductility. Because those electrons aren't fixed in any particular position, that allows the metals to have these properties. Okay? That's a very important thing. And when we get to the solids, you'll see this diagram again, I'm sure. But they like to do diagram comparisons, or they like to give you a diagram in the free response and you explain what type it is based off of what you see here. So, see the positives all in a row like this, and then you see the little dots randomly scattered. That's metallic bonding. They're talking about a metal here. And when we talk about metallic bonding, and maybe you don't necessarily can visualize what I'm talking about, I pull out a sheet of aluminum foil from my lab over there. That sheet of aluminum foil is just a bunch of aluminum atoms that are attracted to one another based off of metallic bonding. So that's what I'm talking about here. Okay? So, you have like a chunk of gold, bar of gold, pure gold. Those are just a bunch of gold atoms that are metallically bonded to each other. Okay? Kind of get the idea? Alrighty. Last but not least, start familiarizing yourself or getting familiar with this table again, because you have to know the properties of the different types of bonding. In general, ionic bonding is going to occur between metal and nonmetal. Sometimes it can occur between the metal and the metalloid. Okay, the metalloids, remember on the staircase, they can kind of go either way. They can bond with nonmetals, they can bond with metals. If they bond with metals, they typically are going to go more in the ionic direction. Okay? So here we would say, you know, this with the metalloid. You have a metal with a nonmetal or a metalloid. Now, if you have covalent where you have the nonmetal, oops, excuse my writing here, say we have nonmetal with a metalloid, that's typically going to swing in the covalent category. So if you see any of the metalloids, if it's bonded with a metal, it's typically going to have more ionic character. If you have a metalloid that's bonded with a nonmetal, it's typically going to be more covalent character. Metallic ones are only going to be metals. Now granted, we're going to talk about alloys, which are mixtures of metals, which are also kind of a gray area. And we'll go into the gray area of that because really they kind of do metallic bonding with one another, but you can still melt them down and separate them by using physical properties of melting point. So that's another fun gray area to look at. Definitely know the way that they form their bonds. Transfer of electrons, sharing electrons, sea of electrons. Transferring of electron, remember, creates the positive, negative charges, the full charges on the ions. That causes an electrostatic force of attraction, that Coulombic attraction. Okay? So, the electrostatic attraction is the Coulombic attraction. For the covalent, we're going to look at a little bit more detail today in the next set of notes in 2.2. That one is also a Coulombic attraction. It's the nuclei, the protons of one of the atoms attracting to the electrons of the other atom. So you still have electrostatic force going on. You have positives and negatives attracting. It's just doing it in a different way. And then, of course, metallic bonding is also electrostatic attraction because you have the positive centers in the free-flowing delocalized C electrons those are attracting to different positive atoms. So you have electrostatic attraction or Coulombic attraction occurring there too. It's just doing it in a different way. The electronegativity difference, okay, should be great. And on some scales, it's 1.8. Some of it, you saw one that said 2.0. It doesn't really matter. You're not going to be asked to calculate it, but just know that it's a great electronegativity difference. The covalents are less electronegativity difference. Now, if you get to a very minimal amount, the 0 to 0.4, okay, that's going to be, you know, pure covalent or nonpolar. I guess I should just write nonpolar. Here, we'll put nonpolar there. Now, the electronegativity difference between metals obviously is going to be 0, so that one doesn't really factor in there. And they do metallic bonding with the delocalized, so it doesn't like, it's not the same kind of thing. Physical state at normal conditions. That's what we mean when we say physical state. Metals and ionic compounds are going to be solids at normal conditions. Okay? And the ionic compound's a lattice structure, which we're going to talk about in just a little bit. For covalent, though, at normal conditions, a lot of them are liquids and gases. There are a few that are solids, like sulfur is a solid, graphite, which is carbon, that's a solid. There's a few covalent molecular solids out there, but a lot of them are gases and liquids. A lot of them are gases. There's a few liquids, I would say, too. So, and that has to do with their IMFs and that they're weaker forces holding them together, but we'll talk about IMFs later. Boiling points, melting points, high for ionic and metallic, low for the covalent, and electrical conductivity. Metals, of course, are conductors as solids. They don't really dissolve in stuff, so, you know, they're just going to conduct as solids. Ionic compounds, though, you can melt them down, but when you melt them down, it's really like molten lava, okay? It's really hot, because the melting points on these things are super high. Like sodium chloride is in like 700 to 800 Celsius, super hot. So it's really like molten. You can melt it down and you can conduct it that way, or you can dissolve it in water and you can conduct it as it's dissolved in water. We say that covalent compounds have no conductivity or they're poor conductors. I've seen it written like that too. They're poor conductors. Covalent stuff kind of falls more into the insulator category, the opposite of conducting. Okay, so definitely familiarize yourself with this table. It's very, very important that you make sure that you know what's going on here.